All right, picture this. You're sitting in your Cambridge IGCSE computer science exam. The clock is ticking down, you read a question about network transmission media, and you quickly scribble down what seems like a perfectly logical, common sense answer. But there is a massive trap waiting for you. So, let's look at this prompt. I want you to play the examiner for a second and spot the exact error in the student answer we're about to explore. This is a super high-stakes scenario. Students literally bleed marks here every single year because they think they're answering the question perfectly, when in reality, they are completely missing the mark scheme's strict requirements. Okay, here is the answer. Twisted pair cables transmit data and are fast. Networks send data everywhere. Now, you might be thinking, well, yeah, that's not technically wrong. But in the eyes of a Cambridge examiner, this is a classic zero-mark trap. Why? Because it's totally void of specific technical points, it ignores the scenario nouns, and it mentions absolutely nothing about the physical layer protocols or the actual physical structure of the cable. Generic answers like this are literally the enemy of a top-band grade. Section 1. Wired Transmission Media Explained. Let's get your transmission fundamentals locked down. We really have to start with precision here. Think of it like this. A computer network is fundamentally just a set of devices, which we call nodes, right? Things like computers or printers, and they're connected through links. But examiners want you to call these links communication channels. When we talk about transmission technologies in this context, we're talking about the physical layer protocols. That means the actual physical methods of sending a signal from one location to another, using things like modulation, line coding, and error control. And this comparison brilliantly highlights exactly what the examiners are looking for. We've got the two most heavily tested wired technologies, twisted pair wire and coaxial cable. Let's look at twisted pair first. You can't just say it's fast. No way. You need to explicitly state it operates between 2 to 100 megabits per second. And why the twists? Because its structure of two insulated copper wires twisted together specifically reduces crosstalk. Now flip over to coaxial cable. It's way faster, hitting 200 to over 500 megabits per second. The structure is totally different too. It uses a copper or aluminum wire wrapped in an insulating layer, all surrounded by a conductive layer. That specific insulation is the magic ingredient that minimizes interference and distortion. Keep this blueprint in mind. It is absolutely crucial for maximum marks. Section 2, broadcast and point-to-point, moving right along. Because it's not just about the wires, it's about how the data moves over them. Transmission technologies basically fall into two camps. First, broadcast networks. Imagine a single communication channel shared by literally every machine on the network. When data is sent, it's sent in short messages, and technically, everyone on that shared channel can hear it. It's kind of like shouting into a crowded room. On the flip side, we have point-to-point networks. These use dedicated connections between individual machines, so it's a direct private conversation between two nodes. No shouting required. To really grasp point-to-point networks, it's super helpful to look at where they actually came from. Back in the late 1950s, early point-to-point systems were used in U.S. military radar systems, like SAGE. Fast forward to 1969, and the U.S. Department of Defense created ARPANET, basically the grandfather of the internet you're using right now. This is a crucial detail because ARPANET relied on dedicated circuit switching. Basically, a single line gets a dedicated circuit for the whole duration of the conversation, much like an old-school two-party telephone call. And that simple, dedicated point-to-point concept, it eventually evolved into the massive, complex internet we all rely on today. Okay, in just a minute, I'm going to reveal a hidden examiner clue that will completely change how you write your exam answers. But first, we need one final framework to make that clue blindingly obvious. You see, copper wires are really only half the story. Section 3, Wavelength Division Multiplexing, or WDM for short. Let's dive in. To really understand that examiner clue and lock down those top band grades, we need to level up to a high-capacity concept that pops up on paper 1 all the time. WDM is arguably the most promising tech for high-capacity communication. But unlike the copper cables we just talked about, WDM is a fiber optic technology. It combines multiple light sources into a single stream. Conceptually, think of it like a massive multi-lane highway, but built specifically for light traveling through fiber optic channels. So let's break down the logical step-by-step process here, because you do need to know the exact hardware involved. Starting at the transmitter side, a device called a multiplexer joins all these different light signals together into one single beam. That combined light then shoots at ridiculously high speeds right through the fiber optic cable. Finally, at the receiver end, a demultiplexer takes that single light beam and splits it right back apart into the original separate light sources. The absolute crucial takeaway here is the massive advantage in data capacity. WDM is custom built to exploit the insanely high data rates of fiber optic cables. If you compare the data rate of WDM fiber optics to the metallic cables, the twisted pair or coaxial ones we just looked at, fiber optics win hands down every single time. Metallic cables are fundamentally bottlenecked by electrical signals running over copper and aluminum. WDM, on the other hand, leverages multiplexed light, which is a total game changer. Section 4. Perfecting your exam answer. Let's bring it all together. All right, here is that hidden examiner clue I promised you earlier. Listen closely. In Cambridge IGCSE Computer Science, generic answers will lose your marks. It's that simple. 1 mark requires one distinct technical point. You absolutely cannot just repeat the same idea. You have to explicitly connect a cable's physical structure to its specific data transmission advantage. And crucially, you must use the exact scenario nouns provided in the exam prompt. So here is a quick, interactive challenge for you. I want you to actively practice this right now. Pause this explainer. Take that flawed 0-mark answer from the beginning of our session and rewrite it. Do it in your head or jot it down on paper. Use the top band terminology we just went over for twisted pair cables. Really think about the speed, the physical structure, and the exact advantage. Okay, let's see how you did. What is so brilliant about this top band answer is how it seamlessly integrates absolutely everything the examiner is looking for. We took that weak twisted pair cables transmit data in our FAST and turned it into this. The LAN uses twisted pair wire to achieve up to 100 Mbps. Its 2 insulated copper wires reduce crosstalk during point-to-point data transmission. See the difference? It's huge. We used a scenario noun, LAN. We nailed down the exact speed, up to 100 Mbps. We detailed the physical structure, 2 insulated copper wires. And we explicitly stated the advantage. It reduces crosstalk. That right there is how you secure every single possible mark. Let's do a super quick, rapid-fire revision of the precise terminology you need to take away from this explainer today. First, networks are nodes connected by communication channels. Second, twisted pair uses 2 wires to reduce crosstalk, hitting up to 100 Mbps. Third, coaxial uses an insulating layer to minimize interference, reaching an awesome 500+ Mbps. Fourth, broadcast networks share a single channel, while point-to-point networks use dedicated circuits. And finally, WDM joins light sources using a multiplexer to unlock the massive data rates of fiber optic cables. Got it? Awesome. So you now know exactly how to describe these technologies perfectly. But here's the ultimate trap. How do you structure a high-level evaluation response when a Paper 1 question forces you to choose between WDM and coaxial for a highly specific, restricted scenario? Trust me, if you don't know the exact evaluation framework, you are going to drop the highest value marks on the entire paper. To get the correct answer pathway and learn that exact framework, you'll want to check out our next explainer. Make sure to subscribe to our YouTube channel, ACE Exams at ACEXams_IGCSE to excel in your Cambridge examinations. Stick around and I will see you in the next explainer.